We constantly hear about parameters, tokens, and these incredibly intelligent models. But behind the curtain of all this amazing software is a massive, hidden physical reality. And that reality is heat. Welcome to this explainer. Today, we're going on a deep dive into the completely transformed world of modern AI infrastructure. We're unpacking a fascinating paper by Alexander Nania, and it argues that AI data center cooling has hit a completely new bottleneck. It's an issue that goes way, way beyond just bringing the temperature down. We're shifting from a world of simple heat removal to this highly complex frontier of dynamic control.
Okay, let's dive into this. 1,000 watts. Now, historically, computer chips pulled roughly 100 watts of power, give or take. But modern AI accelerators, like those in NVIDIA's Rubin-era architecture, they are now just rocketing past 1,000 watts for a single device. Imagine holding a running space heater in a space smaller than your hand. Crazy, right? Well, when you pack dozens of these densely together in a rack, just blowing cold air over them, it physically doesn't cut it anymore.
And wow, when we zoom out to the macro scale, the numbers get even more staggering. We're now looking at hyperscalers, companies like Google, actively preparing for individual data center racks pulling a massive 1 megawatt of power. To put that into perspective, a single rack of AI servers could draw enough electricity to power hundreds of homes. At this sheer density, the era of air cooling is officially dead. It literally just cannot move that much heat fast enough.
So, that brings us to a new, unavoidable reality. Warm water direct-to-chip liquid cooling. It's no longer just some experimental option or a niche luxury for supercomputers, it is the mandatory baseline. It's the absolute backbone required to build dense AI data centers today. By running liquid directly through cold plates attached to the GPUs, we can capture and carry away heat far more effectively than air ever could. But, as our source material reveals, putting liquid on the chip, that's actually the easy part.
Section 1. The hidden bottleneck. Dynamic workloads.
Like I said, getting the liquid to the chip is pretty much a solved problem. But predicting what that heat is going to do next, that's kind of like a detective story where the culprit keeps changing their disguise. An AI data center is not just a steady, predictable space heater. The tasks vary wildly. You might have steady training, which runs at a high, sustained utilization, but then you have bursty inference. Think millions of users suddenly asking a chatbot a question, followed by a total lull. You've got mixed workloads, and even power cap jobs responding to grid events. All of this causes wild, unpredictable heat fluctuations that completely choke static, old-school cooling systems.
Let's move to this next concept and see how it builds. We can trace this problem by following what we call the journey of a joule. When an AI burst hits, the heat first appears at the chip. Then it actually has to move through the package, into the cold plate, through the rack manifolds, out to the coolant distribution unit, the CDU, and finally into the facility's water loop to be rejected outdoors. Every single one of these physical steps introduces delays and thermal inertia. The cooling system doesn't instantly feel the heat that the chip just generated.
Think of the current approach kind of like a massive traffic jam. Running a cooling system at a fixed, high flow rate just to be safe, it's exactly like a driver constantly revving their car engine in stop-and-go traffic. During those inference valleys, the lulls between bursts of AI activity, a static cooling system is pumping aggressively for absolutely no reason. It wastes massive amounts of pump energy and water simply because it's only designed to look at steady-state temperatures, not the dynamic traffic.
Section 2. The solution. Workload-Aware co-control.
So how on earth do we fix this? Well, we need a smart, synchronized hybrid engine. We need to stop treating the computers and the air conditioners as two completely separate things and instead merge them into one intelligent system, Workload-Aware co-control. It's the synchronization of AI workload behavior, GPU power states, the actual flow of the coolant, and the facility's heat rejection. What this means in practice is that a software decision, like scheduling a massive AI inference job in Kubernetes, must directly and immediately dictate the physical behavior of the pumps and valves down in the plumbing. It anticipates the heat before it even reaches the water.
The difference between these two paradigms is literally night and day. Steady-state cooling is reactive. It's conservative. It basically waits for the chip to get hot, panics, and blasts it with a fixed coolant flow, completely wasting energy. Workload-Aware co-control, on the other hand, acts predictively. It knows a heavy job is starting, so it ramps up the pump precisely when needed. This saves both hardware life and critical resources.
When you look at how these benefits stack up, the results are massive. Smarter control actually allows data centers to run warm water loops. We're talking about coolants at 45 degrees Celsius. By safely running the liquid warmer, the facility drastically reduces its reliance on power-hungry mechanical chillers and saves just a ton of evaporative water. And it does all this while keeping the chips safely within their thermal limits. It's an absolute win for energy, water, and hardware lifespan.
Section 3. Building the benchmark.
Now you might be wondering, if this co-control approach is so incredibly beneficial, why aren't we doing it everywhere yet? The simple answer is fragmentation. Everyone is kind of working in their own silo. Hardware vendors are designing racks. AI systems researchers are optimizing job scheduling. The Open Compute project is building great standards, and Microsoft Azure publishes workload traces. But no one is tying it all together. We desperately lack a unified, open way to test and validate these whole system co-control ideas.
So the crucial point is that the industry desperately needs an open benchmark. We need to establish a system boundary that connects workload traces directly to CDU responses and outdoor chillers. And we need to measure that against real-world metrics. Not just, is the chip cold, but how many AI tokens are we actually generating per joule of energy? How much pump energy and water did it cost us to get there?
This requires shifting our entire philosophy. We are literally redefining success. The old metric was simply keeping chips cold at all costs. The new goalpost, maximizing useful AI work, training models, answering prompts for every single drop of water and every watt of energy, all while safely managing thermal risk. It's a holistic view of the data center as a single, breathing organism. Which leaves us with this final, vital thought to reflect on as we witness this massive shift in infrastructure. As AI continues to scale and as the physical demands on our power and water grids intensify, we really have to ask ourselves, is our data center just blindly cooling a piece of silicon, or is it intelligently cooling the workload? The answer to that question will absolutely define the future of AI infrastructure.